All right, share screen. Okay. So hopefully you can see this. Can you see it out okay, Daniel? Yeah, everybody can see the screen over here?
Yes.
Yes, we can see
Yes,
it.
sir.
Yes.
Great. So anyway, so if you go down, so I'll post, so these videos are in S22 videos, and there's 2 posted now. The class we did last on the 18th, and then the one that I recorded for you, that I should have done on Thursday, but I forgot, and so I recorded it, and hopefully you all watched that over the weekend. And then I'll post this one right below this one. All right, so data sheet. So if you scroll down, let's see, I think they're here. So if you scroll down, see, find the data sheet. Yeah, so let's see. Well, that's the old S12 we used to use a long time ago. And they're easy to find if they are on here. I just have to find them. And hopefully you don't have as many things. Okay, maybe they're in the lab folder then. That's probably where they are. All right, so then you go down to labs, pick labs. And so I'll post the, this is the old 4.4. I'll post the 5.5. I have that done. I'll put it up here, but I haven't updated that yet. And then, see, I think the data sheets are down here then. Yeah, pick 16F1825/29 data sheet. That's it. And you pop this open, and I already have it up on, I'm going to skip this. It's better for me to look at it in the Adobe Acrobat, which I pay for, so I have that. But so here's the data sheet, and there's a bunch of stuff up here, but the first page that's useful is to read about kind of the features of the chip, and I've covered some of this, but this kind of reinforces it. And we will use this data sheet extensively, so make sure you download it and have it available on your laptop. And it's really nice if you can also have the index opened up here, so you can just go to whatever file, whatever chapter you need to. And just for reference, we're gonna be working here in chapter 29, the instruction set summary, in just a minute. We're going to go through these. We'll talk about the different types of instructions, and then here are all the instructions. And so we'll go over these, and here's the rest of them. Those 2 pages. That's it. That's all the instructions there are. And yet it can do incredible things with those instructions. And of course, you can write programs in C. They'll be implemented with these instructions when it's compiled. It's compiled into this instruction set. All right.
Professor.
Yeah.
So are we supposed to use that data sheet that you just showed for homework 1, or are we supposed to use the MC9S12 one?
No. The PIC data sheet.
For homework number 1?
Yeah. The S12 was a processor we used for this course when I first taught it many years ago, but not now. I don't even know if I did the S12 then. I think, because even the first year I taught it, I used the PIC 16F1825 then. In fact, I pass out a little bag of parts to everybody, and they actually soldered on the little board. And here is the here's the little board that they put together. We didn't have a lab for the class, so they just did it in class. But some people soldered it like this, and it was it was kind of a disaster. And that's why we went to the printed circuit board, because the point-to-point soldering was just too difficult for students. That having been said, some people that soldered their boards together then have boards that still work. But some people never got their boards working. So it was just a little too challenging. But anyway, yeah, all right. So that's the data sheet though. All right, let me jump into it. So I want to kind of pick up where we were before. And so I'm just gonna kind of go through the programmer's model again a little bit briefly. And then I'm going to start going through the instruction set, and I'm going to explain how the instructions work. But to do that, I will refer back to some of the slides we've already covered. All right. So kind of the learning objectives. I do want you to understand the basic architecture of this 8-bit PIC. I think that's really important. When you study, if you take Dr. Lin's computer architecture class, this will really help you, because you'll see, yeah, he covers the MIPS processor, but which is a different processor, but still it does all the same things. All microprocessors are very similar when you peel them down to the core. So the one of the main sort of architectural divisions between processors is whether they're a Harvard or a von Neumann type. And what that means is, well, can somebody tell me the difference between a Harvard and a von Neumann architecture? Well, anyway, so what that means is, in a Harvard architecture, the memory is divided up. The program memory is separate from the data memory. And in a microprocessor, along with the data memory, we usually put all the registers that control all the peripheral modules. And that's how the PIC's set up. And that's a Harvard type machine. In a von Neumann machine, everything's in the same address space. So when you have a Harvard machine, you actually have a separate data and address bus for the program memory, and a separate data and address bus for the data memory and the functional registers that control the peripheral modules, like the I/O pins, the timers, the A to D converter, and all that. So you have 2 address buses and 2 data buses. And in the case of most chips that are set up that way, the width of the data buses and the address buses is different for the program memory and the data memory. In the case of the PIC, that is certainly the case. The program memory is all 14 bits wide, and so the data bus to the program memory has to be 14 bits wide. The address bus to the program memory is 15 bits wide, which means it can have up to 32K of program memory. Now, our chip doesn't have that much flash implemented. We can only have, we have less than that. I'll tell you in a minute. I always forget a little bit, but that's not something you necessarily have to memorize. I think we have 8K, but we'll double check that in a second. On the data side, our address bus is 12 bits and our data bus is 8 bits. So you can see this allows Microchip to have a different size program memory and word size and address bus size than on the data side, which there are pros and cons to this. On the flip side, in the KL25Z chip, which we use in Micro 2, that chip has a 32-bit address bus and a 32-bit data bus, and everything is in the same address space. So that's another way of going about it. Most of the instructions are 16 bits, a few are 32 bits. Whereas in the PIC, all the instructions are 14 bits in this particular PIC. Even within the PIC world, they do things differently. And even within the ARM core world, some ARM cores are Harvard designed and some ARM cores are von Neumann designed. The M0 Plus and the KL25Z is a von Neumann, but that's the M0 Plus. The M3, the M4, I think are Harvard machines. So they do play around with that architecture a little bit. Otherwise, they almost every microprocessor that I'm aware of has working registers in our case with this PIC, we just have one. Every microprocessor has program counters. And then some microprocessors have to have bank registers, depending on how the address to the memory is set up. The IA32 instruction set that our Intel and AMD chips use for laptops and desktops, they definitely use, they have pages that you have to set up. So they have, there's a page register somewhere. I used to know a lot about that, but at some point I stopped paying attention and spent more time with micros. So I'm not exactly sure what they're doing now, but because when they invented that instruction set, the maximum, they only had 16 bits for the address bus. They've grossly outgrown that. Even a 32-bit address bus wouldn't be sufficient now, because that's 4 gigabytes. It's only 4 gigabytes. And many of your laptops and desktops have 8, 16, 24 gigabytes. So they have to have more address lines. And they usually work those out with a page register or a bank register, that sort of thing. And that's what Microchip does. And I'll go over this in great detail. So I do want you to have a basic understanding of the instruction set, and to be able to write simple programs. You should understand some of the limitations of assembly language. Of course, everything you write for this chip is eventually done in assembly, but it's really nice when you can write it in C when you're involving more mathematically intense programming, because it's very difficult to, it's in assembly language, complicated mathematical programs would just drive you crazy. Just to convert a number from that you type in on the keyboard to an actual binary number is about 40 lines of code. And to convert it back into something that you can display on a screen is the program to do that, which is printf, is about 1,000 lines of code. So there's a lot of work that has to be done in the assembly language world. And then if we start dealing with floating point numbers, it's even more complicated than that. So, and then complicated mathematical functions like sines and cosines. Fortunately, C has library functions for all that stuff. But those library functions, many of them have 30, 40, 50, 1,000 lines of code. So, well, printf is one of the few that has that many, but okay. So I do want you to have a basic understanding of the instruction set. And probably the biggest difference is that the higher level language just gives you some tools that are easy to use, like it's easier to write for loops, while loops, if statements, case statements, to set up data structures and all sorts of things. It's a lot easier in C to do that. And it's certainly a lot easier to write complicated mathematical formulas. Whereas in assembly, everything is you're doing everything 8 bits at a time on this chip. And it's very challenging. All right. So want you to learn about the integrated development environment, MPLAB X. The old MPLAB was just MPLAB, and then they changed that out a few years ago to MPLAB X. So make sure you're not loading up MPLAB, make sure you're loading up MPLAB X. And I'll tell you which version to do. We don't want, we're not going to use the latest version, because in the latest versions, they took out the direct access to the assembler. I guess it's in there somewhere because it has to be, but it's a little hard to write assembly language routines in the latest last 2 or 3 versions. So we'll do about 4
Professor,
or 5. Yeah, go ahead.
are we supposed to be seeing slides right now?
Yeah, you should be. Sorry. Yeah, I switched back and forgot to switch back. Okay, so here's a slide we didn't talk about. So it's good to understand the programmer's model, and this is very similar in all chips, right? All chips have working registers. This PIC chip just has one. They're in the if you take compiler design, you'll see that the MIPS processor has 32 of these general purpose registers. The KL25Z has 13 of them, but really only 8 are available to most instructions. So there's variations on this theme, but they all have working registers. And when you have a lot of registers, then often we'll call it a register to register type machine. Then they all have program counters. So that the program counter functionally always points to the next instruction to be executed. Now, with pipelining, that gets all screwed up because obviously it has to point ahead a little bit because you're fetching 2 or 3 instructions ahead. But forget those details. Bottom line is program counter shows you where you restart in the code. And on this chip, when you branch, you have to flush the pipeline, and then you load in the actual first instruction to be executed when you start your new branch. And that's the same with when you return from a function, then the program counter actually holds the next instruction that you're going to execute. So how they keep that synchronized with their 2 instruction pipeline, that's kind of hidden in some of the internal register logic you don't have to really deal with. We do have indirect registers on this chip, which we're not going to use in the assembly language part. They're certainly available, and you can use them. And if you wrote a lot of assembly language routines, you'd want to learn how to use them because they're very helpful. But for simple stuff, you don't really, I don't know, maybe one of these days we'll do this. It just adds a level of complexity that I didn't want to get into. But this is how all the C instructions are implemented with indirect addressing, and they use the indirect registers. So that's how the C is assembled into that format. And then we have a status register, which holds our condition codes, typically a carry code and a 0 code. And then we also have one other code called a half carry code, which we probably won't use. Some processors have built-in 2's complement overflow bit called a V bit, and often a negative bit as well. But we don't. This chip didn't implement that. And then we have our bank select register. Now the bank select register is going to be very key to your understanding of how this chip works, and that's because the data memory is partitioned into banks. And the reason it's partitioned into banks is because we can fit one whole bank's worth of addresses into our instruction. But since we have, in our case, well, we have 32 banks, we can't, and that's 12 bits. So we actually have 12 bit of address for our data memory. And we only can fit 7 bits of address into any given instruction. So for that reason, the other 5 bits of the address have to be in the bank select register. And to get the full 12-bit address, we take the address, the lower 7 bits that are put in the instruction, and then we have to make sure, as the assembly language programmer, we have to make sure that the upper 5 bits are in the bank select register. Now, if we use indirect addressing, then that changes things a little bit. Then in their actual instruction, we just reference one of the 2 bank select registers. And the bank select register, one of the 2 indirect registers. Then the indirect register actually has the entire address for the data memory location that we actually want to access. And turns out when you use indirect addressing, not only can you access all of the data memory, all of the functional registers for the various modules, but you can actually access all of program memory too, because it's a full 16 bits. All right. So I want you to have a working knowledge of MPLAB X. The old one was called just MPLAB. Make sure you don't get MPLAB. Every single version of MPLAB, MPLAX microchip ever published is available in the archive. So to get the right version, make sure you go to the archive. Don't get the latest version. Go to the archive, and it's I think it's, let's see, what is it? It's, oh yeah, it's 5.35 is the latest version. If you go to 5.40, they take away the assembly language option. And you can't really write an assembly language program. I guess you can, I don't know. I haven't figured out how to do it. They've made it more difficult. One of the things that most microprocessors have, although not all of them, but most of them do, and in some cases you have to deal with them, in some cases they're kind of hidden away from you. They have what are called fuses or configuration bits. And these set features on the chip that are sort of normally not necessarily accessible to you during runtime. So once you flash your program into the chip, these configuration bits are in the Atmel chip. They call them fuses. These fuses are basically hidden from you. And on the Atmel chip, I'm having to set all the fuses so that it'll work with the Arduino IDE. And so we don't want to change the fuses once we get them set to work with the Arduino IDE. On the PIC side, you will have to every time you flash the chip, you have to flash in the configuration words. And we'll talk about that. But we're going to use, with the exception of the Sleep Lab, we're going to use the same settings every time. And there's one setting you have to not mess up, which is the low voltage programming. You have to leave that bit on. If you turn it off accidentally, then you'll have to have one of us take an advanced programmer that can program the chip with high voltage programming and turn the bit back on. So you can use your low voltage programming snap programmer to continue to program your chip. But if your snap programmer can turn the bit off, but it can't turn it back on. That's just how it works. All right. So we'll talk a little bit about the hardware and how the chips are put together, bypass caps, and how we hook up the LEDs, and how we have various interfaces, and how we hook up a switch and various things. And then over time, we're going to go through the functional peripheral modules that are part of this chip, and we'll show you how to use those. And again, they're very similar to the same modules that are on most microprocessors, embedded controllers anyway, microcontrollers. The microprocessor in your desktop or laptop doesn't have built-in functional modules. They have to be added externally by adding external parts to the motherboard or plug-in cards. Okay, so there are 49 instructions. We'll go through these in a minute. And we have up to 32K words of addressable program memory, but on our chip, we don't have that. You could have up to 4 kilobytes of random access memory in this family of PIC chips, but we only have 1K. So a fully filled up chip in this family would have 32K of program memory, a flash, and 4 kilobytes of static RAM. There is a 16-level hardware stack as opposed to a stack pointer that points to random access memory and that gives you, stack space that's only limited by what's in the program memory. This stack has a fixed 16-level stack. That's it. Once you push 16 times, the 17th time, it starts back over at the first push location, and you're overriding something you've already saved, so you're going to have a problem. And then it does have these indirect registers, 2 of them, 2 16-bit indirect registers, which are broken up into high and low, so you can load them 8 bits at a time. Because again, this is an 8-bit processor, so you can really only move 8 bits at once. It does have some nice hardware interrupt features that do what's called content saving. So when you go to an interrupt, it saves a bunch of your registers, saves the working registers, saves the BSR, saves some of the indirect registers, and lets you execute your interrupt service routine without having to first save registers if you're going to use them. And then when you jump back into your program, when you return from interrupt, it restores all those registers automatically from their shadow registers. And so that's a fairly nice feature. It makes the interrupts nice and fast because that's done in hardware. And it does have a fairly, the instruction set's fairly nice. It is a little bit of an enhanced instruction set from the basic, 8-bit PIC world. All right. So we've looked at this before, but just to sort of review it. So here's our 16-level hardware stack. And I guess the program counter also sits over here and some of the reset capabilities. Then here you have your program memory. It's, remember, 14 bits wide. It could be up to 32K, but on our chip, I think we only have 8K. And then here's the CPU that actually executes the instructions. The 14-bit instructions comes over on the 14-bit data line. And then there's an internal oscillator module that can run the chip up to 32 megahertz. It can use an external crystal, an external resonator, an external RC. It can use an internal RC. It can use fairly factory trimmed internal, 2 different internal oscillators, and it can use a phase lock loop, and it can generate a clock as fast as 32 megahertz to run the chip, or that can be slowed down in a whole range of selections for different frequency clocks for different reasons. Faster clocks use more energy. So for battery operated devices, we don't want to have the clock running any faster than we have to. And you can change this dynamically as well. So some of these are software changeable during runtime. There's a little EEPROM with 256 bytes in it that's non-volatile. So if you wanted to save some of your data memory values and then restore them the next time the power was reapplied, you can do that in this EEPROM. Obviously, the program memory is also volatile, but the data memory, it's static RAM, and when you turn off the power, its contents go away. And that's true also for the functional, the registers that control your functional modules. And then here's all our functional modules. Our analog to digital converter, our UART, our touch sensing module, our CCP modules, some of the chips have built-in op amps and all sorts of other stuff, LCD drivers and whatnot. All those things are there, timers and whatnot. Okay, so the program counter, we've talked about this. It's a 15-bit program counter, but it's divided up into the 8 bits of program counter low, PCL, and the 7 bits of the program counter latch high. And when you write the PCL, it puts the upper 7 bits in to give you a total 15-bit write all at one time into the program counter. Now, you don't have to mess with that because both assembly language and C automatically take care of this for you. So in assembly language, you can do jumps and go-tos. Actually, it's a go-to and a branch, a BRA, a branch always. And the actual hardware then will put in the full address by preloading the latch and then dumping it all in when it writes the lower 8 bits so that you get a 15-bit write. There's a little bit of a limit on what the go-to and the branch always can do as far as branching. They can't actually branch from the very beginning of program memory to the end of program memory, but we rarely need to do that. And if you really had to, then you could use this direct method if you really wanted to. But C, of course, takes care of all this for you. In the assembly language world, if you try and jump too far, you could have a problem with a really big assembly language program jumping from the very beginning to the very end. So you might have to worry about that, but we will never encounter that. We're doing. And then, yeah. So again, we talked about the hardware stack already. The working register. So there's one working register. It is 8 bits wide. So that's one of the limits. That's one of the reasons why you only can move 8 bits around, but then the data bus only has 8 wires in it. So you're limited to 8 bits. All the memory locations, of course, are bytes. So 8 bits works. All the functional module registers are all 8 bits. And anytime you move data to memory or from memory, you have to use the W register. You can never write from one memory location directly to another memory location. Now, many microprocessors can do that. That many of them do have that capability, but this one is limited in that regard. It cannot do that. And then, of course, we have indirect addressing, which we're pretty much not going to pay attention to. I mean, if you're really curious, well, I'll talk to you about it. I definitely use it. It's fairly straightforward, but it's just a little more than we need to bite off. We're only going to do about the first four or five labs, and then we're going to switch to C anyway. But this will really help you understand. Yeah, go ahead.
Hi, can I get a papas fritas con carne asada?
Henry, your mic is on. We can hear you ordering.
Hey, order a taco for me, would you? All right. So that's great. All right. So the register that you need to know. So here are basically all the registers that are called the core registers, and these are present in every bank. Again, there are 32 banks, and these are present in every bank. But the only ones that I want you to actually know are the program counter low, the program counter latch high, the status register, the bank select register, and the working register. That's it. Those 5 registers you need to know. The other ones, it's indirect register 0, indirect register 1. These actually aren't locations in memory. They're just names for these high and low pairs of file select register 0 and file select register 1. So these are names for the 2 indirect 16-bit registers. But you actually, when you load up values in these 16-bit registers, you have to do it the low 8 bits and the high 8 bits individually in order to get everything loaded you want in there, because you can't, well, maybe you only need to change the lower 8 bits and that's fine. But you had to make sure the high bits also have the information you want in there. All right. So the first 12 registers in every memory bank are these registers right here. And again, so you never have to bank select any of these registers because they're available in every bank. Okay. So again, here are the registers one more time. The W register has 8 bits. The bank select register only has 5 implemented bits because we need 12 bits for our data memory address line, and 7 are typically in our instruction, and only 5 are needed to be in the bank select. There are only 32 banks, so that's 5 bits. So these bits in the bank select register don't exist. In the program counter is 15 bits. So there's 8 low bits and there's 7 high bits. So it's not a full 16-bit register. Our 2 file select registers are 16 bits. These are the indirect registers, and they have a high and a low byte, so you can load them 1 byte at a time. And then our status register has the three status bits we're interested in are the 3 low bits. There are 8 bits in this register. Some of them are not implemented, but some of the other ones have other functions. Like they will tell us about, they'll tell us about when we wake up from sleep. They can tell us something about how we woke up and how that was. All right. So the bank select register, well, the data memory is partitioned 32 memory banks with 128 bytes in each bank. So if I shift out of this for 1 second, so I'm going to quit, and I go to the data sheet here, and I go to memory organization here, chapter 3, and I scroll down, it'll show you how these things are set up, and it'll also give you a table of all 32 banks. So here is bank 0 through 7, and then here's bank 8 through 15, and 16 through 23, and 24 through 31. So those are all the banks. Now, what you can see is that if we look at bank 0, the first 12 registers here to there, first 12 to there. Those are those 12 core registers. And the 5 key ones you need to know are the PCL, the status, the BSR, and the W register, and the program counter latch high. The INCON register is included, I think. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's included, but you don't need to know that register. We will use it though, but you don't have to bank sell that one because it's also appears. And if you look, you'll see that these registers appear in every bank, all of these registers. But starting with location 13, which is C, starting at 0. So C is 12, but it's actually 13th location because we started at 0. The first 3 here are port ABC. And then in the bank 1, it's TRIS ABC. And in bank 2, it's LAT ABC. And in bank 3, it's ANSEL ABC. And in bank 4, it's the weak pull-ups. So, and then the input level in bank 7. So we do have to access registers in different banks because we have to use the TRIS registers and the latches, the ANSELs, and the ports for our general purpose input output pins. And then we have all the registers that are associated with all the various functional modules that appear after this. And you can see they're all the way bank 7, and then actually there are a few more in here in bank 8. After we get past bank 8, there aren't any more of these functional registers in any of the other banks. They're pretty much gone. The other thing that you should notice is once you get past these, so when you get to 20 hex in each bank, we get into the general purpose registers, are the static random access memory locations. So this is our static RAM. And in the first bank, there are 96 bytes. The upper 16 bytes are 70 all the way to 7F. Those 16 registers are mapped also to every single bank. They're just standard static memory random access locations. They don't have any particular function other than to hold values, but those locations are mapped to every bank. So if you have a few variables you're going to use lots and lots, you can put them in this upper 16 location in the first bank, and then you won't have to use the bank select command to make sure you're in the right bank because they're mapped to every bank automatically. But the rest of the general purpose RAM, there's 80 of those in every bank. So you have 80 general purpose RAM plus these we call these the I forget, there's a name for them now, which slips my mind. But anyway, they're mapped to every bank. But the general purpose RAM, so 80 bytes here, 80 bytes here, 80 bytes here. And then this is actually, this is a mistake. I don't know why they did this. I think they set this up for a different chip. But anyway, oh no, let's see. I mean, oh yeah, no, it's wrong. The actual, in order to get 1K of memory, you have to have these 80 bytes of general purpose RAM have to be in bank 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And then in 12, so there's 40 bytes. I think there's 40 bytes in one of these. They screwed this. This figure's got mistakes in it. But anyway, in later versions, they corrected it. I don't know why I have the old version on this. But anyhow, but after bank 12, then there's no more general purpose RAM because we don't have the maximum amount of general purpose RAM that we could have on this chip. All right. So it's good to know that these banks are all divided up. Now this is, remember, what's in the data memory. In the data memory, we have the core registers. We have the special function registers associated with our GPIO pins and our peripheral modules. And then we have our static RAM. And each bank has the first 12 registers are the same for every bank. And then the next from 13 to well, from C hex to 1F hex, they're the special function registers associated with our modules. And then from 20 hex on in every bank, there are the 90s, they're the 80 general purpose RAMs plus the 16 from the first page mapped to every other page. And you have a total of 1K of static RAM locations. Now, the one thing that you can see right away is problematic. If you have an array that's bigger than 80 bytes, then it's going to span over a couple of banks, and that's going to make it difficult for you to use it easily, because when you go to the next bank, you have to skip past the first 12 plus the next whatever it is. So you have to skip 20 hex of registers before you get to your next general purpose register. And so if you really do need to linearly access a bunch of static random access memory when you're writing in assembly language, then what you have to do is you have to use the indirect addressing. But when you write in C, you don't have to worry about that because C takes care of that for you. All right. So let me switch back to the slides here. Okay. Oh, we call it common RAM. The upper 16 are called common RAM. So that's what we call that. And remember, the common RAM are mapped to every bank. So if you have just a few variables or variables you're using lots and lots and you want to put them in common RAM, that's not a bad idea. It saves you having to do the bank cell instruction, and we'll talk about that in a minute. All right. So basically, so our data memory, including all of our functional registers for our various modules and our core modules, they're all partitioned across 32 memory banks with 128 bytes in every bank. And each bank, again, has that 12 core registers, 20 special function registers, and up to 80 bytes of general purpose RAM. And then at the very top, 16 bytes of common RAM mapped across all banks. 12 core registers mapped across all banks, upper 16 mapped across all banks, but the 20 special function registers and the 80 bytes of general purpose RAM are bank specific. Okay. So indirect addressing uses these FSR0 and FSR1, and you have to load those you have to load the low byte and the high byte separately to get the right address in. And this allows you to get to some special registers. I think you can even get to the locations in the stack. I think you can even read maybe some of the configuration bits through these. I think they even let you get to the hidden registers for context saving for interrupts. So the indirect addressing lets you basically address anything you want to. Okay, but we're not going to worry about this. All right. So this is the bank. This is the status register. So the 3 bits we're interested in: Z bit, the digit carry bit, and the carry bit. We won't really probably use the digit carry bit. This is only involves when we do a mathematical operation. If there's a overflow from the lower 4 bits of a byte into the upper 4 bits of the same byte, that digit carry bit will be set. And what was the purpose of that? The whole idea of that was to allow you to use binary coded decimal to make that a little easier. But we probably won't be doing too much BCD, or maybe no BCD, because when we really do math, we're going to use the C program. Okay. There are 2 other bits in that register that are implemented: the timeout bit and the power down bit. And their function is kind of, it's complicated. The details are confusing, but we'll use this a little bit in the sleep study. Most of the time, you don't really have to worry about these, but if you want to know what woke you up from sleep, sometimes you have to check these bits. Okay. All right. So So this is, so how does an assembly language instruction work? Well, so the way we write assembly language code, so remember there's a little difference between assembly language and machine language. Machine language is what assembly language is translated into. So you write an assembly language code and then, but you write that with letters, you know, with words and some numbers, and that gets translated then into just strictly numbers. And it's strictly the hex digits or the binary bits that are loaded when you flash your chip. That's what's loaded in the memory. But there's a one-to-one correspondence with assembly language instructions and machine language numbers. It's you could actually write the numbers instead of the assembly language instruction if you you know, had memorized all how everything's encoded. But normally we don't want to go to that level because that's doing a lot of work you don't really need to do. All right, so every instruction has potentially has 4 fields to consider. The first field is a label. So we do use labels in assembly language, and the label is the only thing that's supposed to start in the first column. So when you write assembly language code, don't put anything in the first column unless it is a label, the label of a variable or the label of a location in your code. In this case, you can put the label on the same line, but we normally put the label above the instruction just to make it more obvious that it really is a label. And then the next field is called the operation code. And that's the instruction that's going to be executed. That tells the computer, the CPU, what it's going to do. And then the instruction usually, but doesn't have to, there are a few instructions with no operands, but most instructions have at least 1 operand, and some actually have 2 operands. But there's no instructions with more than 2 operands for this chip, but some chips do have that. Some chips have 3 operands and even more. And then if you want to put a comment in, you put a semicolon and a comment. Otherwise, the semicolon is not needed. So in C, you have to have a semicolon after every instruction. You don't have to have that in assembler. You just end the line and start the next instruction. But if you do put a semicolon, it won't hurt anything, and then you can make a comment after that, which is ignored by the assembler. So here's some example codes. We have a bank cell here. Now, strictly speaking, a bank cell is not one of the instructions in the instruction set. It's what's called it's what's called an assembly language directive. And what this does, this directs the assembly language assembler to generate the right instruction to put the upper 5 bits of the address of OSCON into the bank select register. Now, if we went back to our data sheet and we find OSCON. So let's see, where is OSCON? Looks like OSCON, the oscillator control register, is right there. So that would be actually its actual address in data memory is 099 hex. So if you break those bits out, that's actually going to be, it's going to have an address of 19 hex within the bank, but it's going to have 1 bit, the lowest order bit set in the bank select register, indicating that it's in bank 1. So the lower 7 bits of 99 hex will be in bank 1. So if I, just to make that clear, I know that's probably a little confusing. So let me just draw that out, because that would be, I think, helpful to do. See somewhere, where did I put it? Yeah. Okay, let me draw that out temporarily and get a piece of paper. Okay, so if we wrote 99 hex, 099 hex, so 099 hex. Okay, so that's actually going to be 1001, 1001. Okay, the lower 7 bits, 1, 2, 3, 4, 5, 6, 7. So these are the bits that are going to be in the instruction.
Professor, they're not in
repeat-
frame.
Oh, sorry. Okay. Yeah, let me move that like that.
And can you repeat the process? Sorry about that. Thank you.
Yeah, so if we write 0x99 here, okay, so this is the actual hex address in our data memory. Okay, that's our data memory address. But remember, we're going to divide that up into 5 bits in the BSR and 7 bits in the instruction. So these lower bits, 001, 1001. So what we would put in the instruction would be, we'd actually put in this binary number right there. And then in the BSR, we'll put this one. And then the rest of these are zeros. So 1, 2, 3, 4, 5. So the bank's ledger register has to point to location 1. And when we say, and this is the address of OSCON, right? So if we tell the if we do a bank cell instruction, BANK KSEL, what the assembler does, we bank cell OSCON. What the assembler does, it looks up OSCON, finds out its address is hex 099, takes the lower 7 bits, and then it takes away the lower 7, it looks at it, and it looks at the bits 8, 9, 10, 11, and 12, and it puts those bits, it makes an instruction to put those bits into the bank select register. And to do that, it uses an instruction we'll look at in just a minute, which is called an MOV literal to the bank select register. And in this case, it would put 0x1, or just 1, or if you did binary, it'd be 00001. So that's what it actually does. It actually makes this instruction for you. Now you could just make that instruction yourself, but then you'd have to know that the OSCON address was 099, which is a bit of a hassle to have to look that up, since you wouldn't remember everything probably. And so it's easier just to write bank cell OSCON and let the assembler do that work. All right, is that clear what happens there? All right, so there's a lot of details you have to sort of appreciate kind of at the beginning for it to make sense. All right, and then let me see. Did I do this? I did this. Let me just get rid of this. Yeah. All right. So, and the IDE will do this formatting for you automatically. If you just hit this tab every time you do a thing. So again, the format, if we have a label, it starts in location 1. Otherwise, don't put anything in location 1. And then we have an opcode. Then we have an operand. In this case, our operand was the OSCON. Now, this is a compiler directive, not an instruction, but here, MOV literal to W 06A, this is an opcode. And then this is the first operand, and there's not a second operand. And then we have a semicolon, and we finally have our last field, which is a comment. Set for 4 megahertz internal clock. All right, so that's what we're going to do. We're going to put 6 alpha into the oscillator control register to set us up for 4 megahertz. Now, how would we know that? Well, good question. So what we have to do, we have to go back and we have to look at the oscillator control. So here we are, oscillator module with fail-safe clock monitor. Okay, we click on that and we scroll down, and eventually we'll see that we've got all these choices we can make, and we'll finally find the registers that actually run this module as we keep scrolling down, and it describes all this. And I'm going to have you read through this. When you read through it, you know, stuff like this, just kind of glance at it, scroll by it. Don't spend a lot of time trying to study this, but read these little paragraphs. And if it doesn't make sense, that's fine. Just scan through it then. But I think you'll find it sort of interesting, if not a little confusing. And it'll talk about a number of features. Finally, it's going to get down to the control registers that you use to control this module. And the OSCON is the primary control register, and there's several others as well. And this register has 8 bits, bit 0, 1, 2. Bit 2 is not implemented, it's grayed out here, but you have the first 2 bits are implemented, and then bit 3, 4, 5, 6, and 7 are all implemented. Bit 7 describes what it does here, and this is called the software phase lock loop enable bit. Okay, now they don't usually explain these abbreviations, you have to figure them out, which is kind of irritating. That's the way they do it. So software phase lock loop enabled bit. And it does tell you software phase lock loop enabled bit, so you can kind of figure out what the letters mean there. And then if the configuration word enabled the phase lock loop, then this bit's ignored. But if your configuration word did not enable the phase lock loop, then you can enable it and disable it in software by clearing or setting this bit. And if it's set, that enables the phase lock loop. And if it's cleared, it disables it. And the phase lock loop is required for some of the settings that you might want to choose. And then some settings, you can do it with or without the phase lock loop. We're going to run it without the phase lock loop being enabled, but that does mean we can't hit the maximum speed of because of that, which is 32 megahertz. But to get to 32 megahertz, the phase lock, we have to put in this value, and we also have to make sure that the phase lock loop is enabled. All right, so that 7th bit works only if the configuration word is equal to, for that bit is 0. Otherwise, it ignores it. Then the next 4 bits, 1, 2, 3, 4, are called the IRCF field, 3 through 0, and it's bits 6 through 3. And these are the values we want here. It turns out we're going to run the chip at 4 megahertz. 4 megahertz is just kind of a good compromise frequency to run it at. You can run it if you need to go faster, you can go to 32 megahertz. That's fine. And occasionally there might be a reason you want to go slower, but generally this is a good compromise speed. And so that's what we're going to do. And in order to do that, we set it at, we put in the bits for those, we put in the bits 6 through 3 here. We put in 1101. So if our phase lock loop bit is a 0, and then we do 110, so that's so it's 1, so 0, 110, so that's 6, and then we have a 1 here, 6 hex. Then we have a 1 here. This is unimplemented, and then down here we have to look at this field. We're going to use the internal oscillator block, which is 1x. So don't care. So you could be 1 1 or 1 0, and we'll just do 1 0. So that'll be 0 1 1 0 1 0 1 0. So 6A is the hex value that represents that bit pattern, and that's why we use 6A. Then here, let me shrink this down. So that's why we put 0x 6A in here, and that sets us for 4 megahertz. And then we first put this 6A hex into the W register with this instruction, and then we write it from the W register into the OSCON register with this instruction. But we have to make sure before we do this that the bank select register is pointing to the correct bank for OSCON. Otherwise, we would write that somewhere else. And you can actually see where else we might write that rather easily. If you look back at our data sheet and we go back to our memory organization, and we go down back to where the bank select registers are all splayed out here. it turns out, so OSCON's right here. If we left the bank cell point at 0, that would be the timer 1 gate control register. That wouldn't help us. And here's our digital to analog converter control register 1. Well, that's not going to help us. And here, this would be the UART receive register, control register. And this would be the SSP2 buff and all sorts of stuff. So you have to make sure you're pointing to bank 1, or you're not going to write it right here. You're going to write it in one of these other locations, wherever the BSR happen to be pointing. Okay. So we'll shrink this back down. All right. So here are instructions. Now I think I'm gonna deviate from the slides and go back to the data sheet, because it's in the data sheet as well. It's basically just as good in the data sheet. So if we go to the data sheet down here to 29, and we scroll down just a little bit, the first thing we see is we have this figure 29-1, which shows the general format for instructions. And then you'll see we use some little codes in here, D, F, B, K. And so we want to go up here and make sure we know what these little bits mean. So F stands for a register file address. So that's one of our data memory locations. W always stands for the working register. B stands for a bit address within an 8-bit file register. So that could have a value of 0, 1, 2, 3, 4, 5, 6, or 7. And then K is a literal field, which is a constant data or a label. And then X is a don't care. And then D is this destination bit. Now this is really important. I want you to really pay attention to this D bit. It's a single bit, and it can only have a value of obviously 0 or 1. If it's a 0, then our destination is the W register. And if it's a 1, then their destination is whatever the F of the instruction happens to be, the file register that instruction references. So this D bit is the key to understanding one of the complexities of this instruction set that confuses a lot of people. So remember, the D bit is a single bit. It's either 0 or 1, and it only refers to either the W register or the F that's referenced by the instruction, the file register that the instruction's referencing. So in the case of the code we just looked at, OSCON would have been that file register. So we didn't use a D bit there because the instructions that we used didn't have that second operand, but most of the rest of the byte-oriented instructions do. All right, so let's go look at the instructions or the formats. The byte-oriented file register operations all have an opcode that tells what that instruction is going to do. It has a D bit that tells whether to leave the result in the file register referenced here or in the W register. And we have a bunch of those. And then there's a few then we have what are called bit-oriented file register operations. And this has an opcode. It has a B field, which is a 3-bit field, and it has a file register. Now, when we actually write the instructions, we write the F first, and then we have a comma, and then we write the D, we write the F first here and a comma and a B. So this is not the order we write it, but this is how it's stored. And then we have these literal instructions, and we have an opcode, and then we have a 8-bit byte, a literal value that's essentially a constant we're going to use. And it's just 8 bits, it's all it is. And then we have our call and go to instruction, where we have an opcode and we have 11 bits of literal address, which since we have a 12-bit, since we have a 15-bit address line for our program memory, 11 bits is not going to get us from one end to the other. It'll only move us, partway through it. So that's why you do have to sort of pay attention. If you're going to do a really long jump, you have to make sure that 11 bits will get you there. But that would be for a really large program. And again, we don't have 32 bytes of flash. We only have 8 bytes of flash. But even 8 bytes of flash is slightly bigger than 11 bits. It's actually 9 bits, I think. So you could have a problem if you had a very large assembly language program. All right. And then we have this MOVLP instruction. And this is used to write a 7-bit literal into the program counter latch high. Then we have this MOVLB instruction. This is used to write a 5-bit literal into the bank select register. And this is the instruction that the bank cell compiler or the assembler directive actually creates for us. So you don't have to worry about writing any of these instructions because you just have to use bank cell instead. And then we have this branch always instruction instead of the go to. I don't know why they have this. Instead of 11 bits, you only get 9 bits, with the BRA. But for short jumps, it works fine. But you probably should just always use the go to. And then we have these two that are associated with file select register offsets. When you do indirect addressing, you can include a literal offset, and then you can also include an increment if you want. And these are basically used by the C language compiler. We're not going to use these format of instructions. And here finally, there are a few instructions where there's just an opcode and no operands or anything else. Okay, so here are the instructions. So these instructions are the byte-oriented file register operations. They usually deal with an entire byte in a file register, and they're the format of the first 1 or 2 or 3 we looked at already. So and here's how they work. They have a mnemonic, which is the name of the instruction. In this case, add W to F, add W to F with carry, add and W with F, arithmetic shift right F, logical shift left F, logical shift right F, clear W. You see, clear W doesn't even have any operands because you're clearing the W register. Complement F, decrement F, increment F, inclusive or W with F, move F. And what that does, this move F is a real important instruction. It takes a value in memory and moves it to the W register if you specify the D bit as a W or a 0. If you specify the D bit as an F, it doesn't move anything anywhere, but it does set the Z bit for you if the location at F is a 0. So that's one way to test a file register to see if it's 0. If you make the D bit a 1. Here we have move W to F. Now notice this one does not have a D bit. All these other ones except the clears had a D bit, except the move W to F and the clears. But when you move W to F, you take the contents of the W register and you move it to the specified file register, some memory location or whatever. Usually you have a variable name you're using, or it could be into OSCON, which is what we just did, or some other register. Then you have rotate left through carry, rotate right through carry, subtract W from F, subtract W from F with a borrow, which means you use the carry bit. Swap nibbles. This is not swap bytes. This only swaps the lower 4 bits with the upper 4 bits in a single instruction. Sometimes students have tried to use this to swap a byte in one location with a byte in another location, and it's not for that. Remember, it's got one file register, and then it's got this D bit, which is how many bits is the D bit? Somebody tell me. See if
1 or 0.
That's right. It's a single bit. 1 bit, it can only be 0 or 1. So it's obviously not going to be 7 bits of address for a second file register. And then we have exclusive or W with F. And here's F specified. And you leave, for all these other operations, this D bit tells you whether to leave, like when you exclusive or W with F, you can leave the result in F, or you can leave the result in W, which is a really nice feature. All right. Now we have byte-oriented skips. These are how we implement our for loop. We use the decrement F skip on 0. I don't really ever use the increment F skip on 0. it works basically the same, except this is going counting down and this is counting up. And when they overflow, then or when you count down to 0 or you overflow to 0, counting up, then you skip. And this whole skip way is the way all the branching gets done. And again, it has a D bit, which tells you where to leave the result. Now, normally we want to, most of the time we want these D bits, we want to leave the result in the file register, most of the time. But we might want to leave it in W sometimes. In the case of this decrement F skip on 0, we do want to leave it in the file register, so D should be 1. Now, the interesting thing, if you look up here, you'll see default on the D bit is 1. So if you don't specify, it gets left in the file register. So if you try and do a move F instruction here and you want to load a value into the W register from memory, but you don't specify, where's the move F? But you don't specify the D bit to be a 0, it will assume it's a 1 and it will leave it in the file register and it won't move a thing. It'll just test it for 0. So you got to remember to use the D bit. Here, if you in the decrement F skip on 0, if you want to leave it in the file register and you forget it and leave off the D bit, it'll still work correctly because it'll leave it there by default, but in the file register. But when you want it in W, you've got to specify it. All right. Now, this bit clear F and bit set F, we're going to use these a lot, and you're going to be really sad that you don't have these in you don't have those commands in C. You'll actually like these and you'll miss them. But what this does, like if you want to change bit 3, if you want to clear bit 3 in say port A, then you would say BCF. Well, first you have to bank cell port A to get it, the bank select register set correctly. But then you would do BCF port A, comma 3. And you can pick any bit 0 through 7. Remember, first bit's 0 and the last bit's 7. And this B is a 3-bit value. So you get to specify 0, 1, 2, 3, 4, 5, 6, or 7. And then you can set the bit. This is how we'll blink the LED. We'll do a bit clear F to turn the LED on, and we'll do a bit set F to turn it off using the right, well, we'll use the latch register for this. And then this is how we also can set up, we can pull on a bit, wait till a bit, we can wait till the module finishes whatever it's doing, it'll set or clear a bit, and this allows us to do this. This is called bit test F skip clear, bit test F skip set. All right, and then let me just cover these literals, and then I think we'll quit with this. And then on Thursday, I'll go through the actual routine, which I didn't really get to. Maybe I'll flash that up. But all right, so the literal operations, I kind of talked about these a little bit already when I went through the types, the format of the instruction. The ones that you're interested in primarily are the ones that deal with W. Add a literal to W, and a literal with W, inclusive or a literal with W, move a literal to W, subtract a literal from W, and exclusive or a literal from W. And then the two kind of oddballs here are move a literal to the bank select register, and that's a 5-bit literal, and move a 7-bit literal to the PC latch high, the program counter latch high. So those are kind of different, but the rest of these all deal with W. And the one we'll probably use the most is move a literal to W. When we want to load 6 alpha into the OSCON register, we first have to move 6 alpha into W, and we use this literal instruction so that the 6 alpha lives in this instruction itself. And then once you put it in W, then you write the W register out to the OSCON. Okay, so let me share my other screen real quick and see if this will, oh, maybe that won't work. Okay, hang on. Okay, cancel. Oh, sorry, you can't minimize it. Well, how? Oh, okay, I can shrink it though. Oh, okay, there we go. I can move it over here. All right, now let me share again. So here's MP Lab X, and oh no, it's not. Okay, let me try that again. Share screen. Okay. Won't let me share that screen. All right. But you can see MPLab X now, right? Yes. Okay, so anyway, so this is our program, and we're gonna set this up. I'll go through this on Thursday. I'll kind of show you how to do the configuration words here.
Oh, sir, we can't see your screen.
You can't see it?
No,
What are you seeing?
we're seeing your lock screen or your home screen.
Okay, let's try it one more time. It's kind of behaving weird, but okay, let's do this. Now, can you see this over here?
Yes.
Okay. Yeah, I don't know what, that's crazy. Okay. So this is MPLab X. And so I started a little blank program here, but I will go through and finish this on Thursday. We'll talk about it because we're kind of out of time. All right. So let me stop. Were there any questions?
Do you want us to download MPLab X until Thursday?
Yeah, you can wait. So I want you to make sure you download the right version. And so let me make, so just hold off on that. If you want to do it, you can do version 5.35 or earlier, but don't do anything later than 5.35. And it should be MPLab X, not MPLab.
Okay, thank you.
Yeah, and you have to go into the archives to do that. And it's not that difficult to find them, but they're a little tricky to find your way to the archives. And then we'll also do XC8, the C compiler, but there's a certain version of that we want to do too. We want to do, I don't know, I forget. I'll give you all that information on Thursday. So no panic. It's going to be a little bit, it'll be next week before we're writing programs. But we will. All right, any other questions? All right, that's very good. All right, so we will we'll pick up then on Thursday. I'll do two things. I'll go through how we're going to write the first Blink program in detail, and this will really help you begin to make sense out of the instruction set. I know right now a lot of information, and a lot of it doesn't make a lot of sense, and that's just, I don't know. It's the hazard of learning something complicated, but it'll all sort of come together. It'll make sense to you. It's not that difficult, and you'll feel pretty comfortable. Some of you will even like assembly language a lot, but then when you get to C, it won't take much to subvert you to C because it's so much more powerful. But and I know all of you've taken some C, so but it's kind of fun to see how the chip actually works. That's the whole point. Okay. With that, we'll quit. We'll see you on Thursday, and hopefully then we will be in lab on Friday, and we will have 90 boards and hopefully 90 snaps to pass out. So we'll see you then.